Good day. We are going to look at how to solve trig equations. Solving a trig equation really is like anything else. You have to follow a series of mathematically legal steps to isolate the variable for which you're seeking a solution. That's going to hold true whether you're solving 2x plus 5 equals 3 or whether you're solving something really complicated with derivatives and integrals. Mathematically legal steps are things like you can add or subtract whatever you want so long as you do the same thing to both sides. That's always possible. You can multiply or divide everything on both sides of the equation by the same value, but just remember 0 is not a value we like to use because multiplying by 0 wipes everything out and division by 0 is not allowed. That's an illegal thing. But we could double everything in an equation, so long as we do that to every term on both sides. We can use properties of functions to combine, to separate, to change. Think back to when we solved log equations, how we would use our log properties to combine logarithms into one log of something equaled something. Or if we use square root of 10 divided by square root of 2 to get square root of 5. It's using our properties to make things easier. We're allowed to do that. If your variable is trapped inside of a function, we need to get that function alone on one side so that we can use the inverse for that function to free our variable. So for example, if I have my x trapped inside a square root, I'm going to get rid of everything outside of that square root and move it to one side of the equation so that I can square both sides. If x is trapped inside absolute value, I'm going to get rid of everything outside of absolute value, move it to one side so I can then split into the two possible answers. Same with trig. If I have something trapped inside of a trig function, I need to get that function alone. And what's really important is to have only one type of function in a problem. So if I have cube root and fourth root going on, maybe I want to switch those to their fraction exponent form and do some magic to try to get it to only one kind of root. With trig, I really would like to get it down to only one kind of trig, like sine or cosine or tangent, not a mix with sines and cosines or tangents and secants. And of course, as the equations get more complicated, especially when you start using inverse functions, you really should always check your solutions. First things first, do they make sense? And then, is there the possibility of an extraneous solution? Anytime you use a function that by itself is restricted, for example, square root cannot be done on a negative number, you want to make sure you check your answers because if you used one of those, it's possible that you'll get an extraneous solution as a byproduct. And of course, did you find everything? Sometimes you're asked to find solutions within a particular domain. You want to make sure you've found them all. So let's focus solely on trig equations. I thought if I solve the equations here like this and just walked you through, it might be a little easier to follow. So we're going to be solving equations today in a domain of 0 to 2 pi for theta, so once around a unit circle. Let's start with this trig equation. 1 minus 2 tangent squared theta equals negative tangent squared theta. On this side of my table, I'm going to show you mathematical steps. On the other side of my table, I'm going to give you the what and why. So on this side of my table, I'm going to start by adding 2 tangent squared to both sides. I noticed that there was tangent squareds on both the left and the right. Adding a 2 tangent squared will get them together and will make it positive. So I went ahead and did that and I got to 1 equals tangent squared of theta. Now, when I have a tangent squared, one of the things I would need to do next is then take a square root of both sides. So I did that. And you can see that I had to account for having both the positive and the negative option. So tangent theta could have been 1 or negative 1 and still produce a 1 when squared. Now that I have it down to tangent theta equals 1 or negative 1, I'm ready to go. I head to my unit circle because I do know that tangent exists on my unit circle. So I'm going to go around the unit circle and say, where is tangent theta equal to 1 or negative 1? Well, between 0 and 2 pi, or once around the unit circle, that gives me 4 possible answers. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. What I'm going to do now is I need to check all 4 of those solutions in the original equation. Now, I am not going to require that you would show your work like I'm going to show here. Most of the time we check these by just doing the math, and if it works, we're good. But I want you to see how that solution process worked. So here I plugged pi over 4 into the original equation. And it turned out that it worked. I plugged in 3 pi over 4, and it worked. I plugged in 5 pi over 4, and it worked. And 7 pi over 4, and it worked. So all 4 of them checked out okay, and so there are the 4 solutions. My theta, let's fix this right here. My theta is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Let's do another example, and we'll make this one a little scarier. Here I have root 2 cotangent theta minus 3 secant theta equals cotangent 3 secant theta minus 3 secant theta. If your first instinct on this one is a momentary panic, you are not alone. There is a lot to find very anxiety-driven about this equation. There's a square root of 2, and we have a cotangent, which is not on the unit circle, and we have a secant, which is also not on the unit circle. So let's see if we can try to make our life easier here and get it back to things that we know. First thing I noticed when I read through it was there was a minus 3 secant theta on both sides. So if I add 3 secant theta, like I showed right here, that's going to make it go away. Anything going away is a good thing. So I'm left with this. Now, having cotangents and secants is a bad thing. This is not going to work for me because I really need just one trig thing, a cosine or a sine or a tangent, and especially those 3 because they're on a unit circle. So what I'm going to do is I'm going to use my properties to change out these less familiar trig ratios to something more familiar. Cotangent is cosine over sine. Secant is 1 over cosine. In doing that, my right side has some cosines that eliminate, and I'm left with 1 over sine. On the left side, I'm going to move that root 2 multiplier to the numerator because that's where multipliers live. So that gets me to here. Now, it would be super tempting to say, let's multiply both sides by sine theta. And practically, while that might work, we really don't want to multiply or divide both sides of an equation by functions because functions often have various little idiosyncrasies or things about them that we have to watch out for. So in this case, why would multiplying by sine theta be a problem? Well, because there are values of theta for which the sign would be 0, and multiplying both sides of an equation by 0 would be bad. So here's what I'm going to do. I'm going to come over here and say, look, if theta is 0 or pi, then sine theta would be a problem. Let's just assume then that 0 and pi are not going to be solutions. So then I could multiply both sides by sine theta, or I could even say the denominators are equal. Therefore, the numerators must also be equal. So now I just have cosine. Awesome. If I divide both sides by root 2, and then, of course, gotta rationalize, I get cosine theta is root 2 over 2. That seems pretty familiar. I'm going to head to the unit circle and see where does theta produce a cosine of root 2 over 2. And that's positive root 2 over 2. Aha, I got pi over 4 and 7 pi over 4. Well, that wasn't 0 or pi, which is what we said was forbidden. So we just need to double check. And keep in mind, we always go back to the original equation, just in case something we did along the way caused a problem. So I'm going to head back. Over here, I did a little bit of side math. Secant of pi over 4 was cosine, or 1 over cosine pi over 4, and so I did a whole bunch of math. I thought it'd be easier to do this math over to the side. And just remember, any variant of pi over 4 is going to have that same value, just the right sign for the quadrant. Just like any version of pi over 4 has a cosine of root 2 over 2, but sometimes positive and sometimes negative. So I plugged in pi over 4, I swapped out all of my numbers, and it worked. And then I did the same thing with 7 pi over 4. I swapped everything out, and it worked. So there we go. 2 solutions, good to go. All right, let's tackle another one. I have sine squared theta plus 2 minus cosine squared theta equals 3 sine theta. Now my biggest issue is I see a mix of sines and cosines. And I really feel like with sine squared going on in this problem and plane sine going on in this problem, it starts to feel like I'm heading in a quadratic equation direction. So I really think cosine squared needs to leave. I'm going to use our Pythagorean property. I know that cosine squared is 1 minus sine squared. So I'm going to go back to my equation and I'm going to change that out. So here it is. I did the change out. Since I was subtracting that, I had to distribute a subtraction. And then I went ahead and got my sine squareds together. I'm left with only sine theta in some form. So looking at this is just feeling so quadratic. Now, if you're able to see the quadratic equation here and solve it, by all means, go for it. But sometimes it's hard to see that when you're also looking at sine. So I'm going to use a little trick, the U substitution. I'm going to change every sine theta into the letter U, just so that I can see what's the underlying structure of the problem, rather than trying to look at it all at once. By changing it out, yep, I can see this is quadratic. I would move that minus 3u, or sine if I kept it in sine form, over to the left. Now I can factor, now I can solve. Well, if I go back, I said that a u was sine theta. So I can switch back to my original problem. Sine theta is now a half, or sine theta is 1. So we go to the unit circle. Where would that happen on my unit circle? That would happen at pi over 6, 5 pi over 6, and pi over 2. Again, we didn't do anything crazy. I didn't square, I didn't take a root, I didn't divide or multiply by something strange. This seemed pretty straightforward. I really do expect all 3 of my solutions are going to work. I'm still going to check though. You never know. Better to be safe than sorry. So here we go. I checked my first one, and it was good. I checked 5 pi over 6, and it was good. I checked pi over 2, and it was good. So all 3 of my solutions checked out. And if I wanted to, I could go ahead and put that here, my final statement. Theta is pi over 6, 5 pi over 6, and pi over 2. All right. Now, with this next example, I just did the math. See if you can follow it through. Go ahead and pause and read through the entire equation and see if you can follow it through from start to finish. And then come back and I'll explain it. All right, so the first thing I did is I subtracted 3 sine theta to try to get all my sine thetas to one side. So I got 0 equals root 3 sine theta plus 3 cosine theta. Oh, see, my 3 sine theta is subtracted off. Now with both sine and cosine, just plain sine and cosine, I'm not so sure I'm going to be able to switch one into the other. And that root 3 and that 3 are really seeming familiar. So when I looked at my unit circle, I noticed that root 3's tended to come up with tangent. And I know sine and cosine can make tangent. So I went ahead and moved the sine back to the left, and then I divided both sides by cosine, and I divided both sides by negative square root of 3. I am going to assume that my cosine is not 0. So that's important. I'm just going to say assume cosine does not equal 0, therefore I can divide by it. After doing a little rationalizing, sine over cosine is tangent. I did my rationalizing, I got that then tangent theta is negative root 3. Aha. Go to my unit circle, there are 2 places that happens. And then I check my work, and in both cases, the solutions checked out. All right, so now we are going to let you try this on your own. So here is an equation. Go ahead and try solving it by yourself. And then when you're ready, you can take a look. I'll scroll my page down and show you the solution. Pause now. Welcome back. Here's the solution. So I decided, like we did at the very beginning, better to change secants and cotangents into their sines and cosines. And in doing so, I ended up with root 3 over cosine theta plus 1 over sine theta was 0. And then I got stuck. And I'm like, dang it, that didn't help. Because now I have different denominators. I'd have to do a whole common denominator thing, which would be sine times cosine, and that just gets messy. So then I went to another attempt. I noticed that it equaled 0. And since we did a quadratic equation earlier on here in this lesson, and I know that quadratic equations, when they equal 0, if you can factor, maybe I should try factoring. You know, you can actually factor secant theta because it really is just a number. So I factored out secant theta. Oh, wait a second. I have secant theta, a quantity, multiplied to root 3 plus cotangent theta, another quantity, and it equals 0. Oh, that's the good old zero product property. That means that if that product was 0, either the secant caused a 0, or it was that root 3 plus cotangent that caused the 0. So I'm going to separate that out now into my 2 possibilities. Either secant theta was 0, or this one was 0. So let me solve this one first. I know that secant is 1 over the cosine. Oh, hold up. Wait a minute. How can I take 1 and divide it by anything and get 0? There is no solution to this side of the problem. I will get no answers out of this, so I'm going to abandon this and go to the other side. Subtract my root 3. I remember that cotangent is 1 over the tangent, so I'm going to do the reciprocal of both sides, since there are no adding or subtractings going on here. And then I'm going to rationalize because no root 3 is allowed in the denominator. We know that. So I'm going to rationalize. And then I went to my unit circle and I looked where were these tangents happening. And they were happening at 5 pi over 6 and 11 pi over 6. I went back, I checked both answers in the original problem, and they both checked out. So that is your review for how to solve trig equations. Trust me, this takes practice, and like this one, sometimes it takes a couple of false attempts before you hit upon what works. I will tell you that the more you solve these, the more tricks you learn and the easier they will get. but it's okay if it feels really hard right now. Good luck, and go ahead and do some practice.